It's Alfred, the airsick eagle, never liked being up high. Okay, we are here looking at gravity problems. This is number 46 if you're following along with the class. Otherwise, just a random problem. And what we're looking at here is some angular momentum ideas. What we have is Halley's Comet, which is one of the most famous comets that kind of goes around our sun. It passes every 76 years, so you'll probably get to see it once in your lifetime if you're just normal, twice if you're lucky. Maybe you get it once when you're young, once when you're old. And it has a highly elliptical orbit, a very highly elliptical orbit. And when closest to the sun at perihelion, para meaning closest, helion meaning our sun, it is at a distance of 8.8 times 10 to the 10th. That didn't really format right there, did it? So that's times 10 to the 10th meters. And it's moving with a speed of 54.6 kilometers per second. The greatest distance between Halley's Comet and the Sun, aphelion, is 5.27 times 10 to the 12th meters. So the question is the speed of Halley's Comet greater than, or less than the 54.6 kilometers a second whenever it's at aphelion? Explain. Can I ever talk? Jeez. Okay, so let's draw an ellipse real quick. This is a highly eccentric ellipse, but it'll get the point across. Here is our sun. When Halley's Comet is at closest approach here, it has a velocity of 54.6 kilometers per second. That is super fast. Okay, it's zipping around the sun. It is also at this closest position, so we'll call this RP, the distance of perihelion. Whenever it is way far away, all the way out here, this is the aphelion point, and it still has a velocity out here. But if we think about this, the comet is like falling in towards the sun, but it misses the sun and it zips around. And as it's falling out, it's like being thrown away from the sun. It's kind of like you throw a ball up. It's slowing down as it moves out until it gets to this furthest away point. And when it gets to the furthest away point, it has the minimum speed, and then it's going to fall back towards the sun where it will speed up. Okay? So when it gets out to this farthest point, it is going to have a lesser speed. It's actually going to be its minimum. And we can think of this as, the object is falling away from the sun. The gravitational force from the sun is pulling back on it. It's going to accelerate it in a negative direction, or at least a component of the acceleration is pulling it in a negative direction. And the object will slow down. Okay. We could also, if we wanted to think about this in terms of angular momentum, if we wanted to describe that, which we're going to use for part B, but we can say that as angular momentum is conserved, the position of this object going way out here to the radius of aphelion, that position is much further away, so with angular momentum being conserved, the velocity must slow down. And let's show that mathematically. We actually did this last unit in rotation, but whatever we have initially for our angular momentum has to be what we have finally for our angular momentum. And I showed this in one of our videos, but for a point mass, which is what we consider planets, comets, moons, suns, we can say that the angular momentum, which is I omega, a point mass means that the moment of inertia is just mr squared. So we get mr squared, and this omega here we can rewrite, if you recall, we can rewrite this omega as a velocity over a radius. And these are all initials. So this is the, let's call this like perihelion, and that's just the mass of the object. And if we do this for the other side, this will once again just be mrv, but these are all the aphelion distances. And what we quickly see is that the masses on each side are the same. So we just have the equation that the radius at perihelion, or the distance at perihelion, I should say, multiplied by the speed of perihelion equals the distance of aphelion times the speed of aphelion here. And that is the conservation of angular momentum. We're just looking for the speed at aphelion, and we actually have the velocity. That was the 50-something kilometers per second. We have the radius right here, 8.823 times 10 to the 10th, and we have the radius here, or rather the position, I keep saying radius, I mean position, of 5.27 times 10 to the 10th. So we can solve for that unknown. We just got to shove in the numbers. So let's kind of just write this out real quick. 8.823 times 10 to the 10th times the velocity of, and I'm just going to get my final answer in kilometers per second. I'm just going to leave it in kilometers, so my answer will be in kilometers. That will be 54.6 kilometers per second. And then maybe I see this above. I'm just going to divide each side by RA. So that means what I can do here is I'm just going to divide this by RA, which for our setup here, 5.27 times 10 to the 10th, 10 to the 12th, 5.27 times 10 to the 12th, meters, the meters go away, which is nice. And this gives me my velocity at Helion. Now we just got to shove in all the numbers. So 8.823 times 10 to the 10th times 54.6 divided by 5.27 times 10 to the 12th gives me an answer of 0.914, and my only units left are kilometers per second. So that's what I get there, okay? Not too crazy of a problem. We're just talking about what's going on and then applying a conservation of angular momentum, which we saw back in our unit of rotation. Using this equation right here and just kind of solving for the unknowns based on what we put in, we get this lovely little answer. And we kept it in kilometers just because that was the easiest thing to do because we already given it in the kilometers there. So still very, very fast, but almost just a little bit under a mile, maybe like 0.6 miles every second. So very, very fast. Halley's Comet's moving whenever it is very far away, and it's moving way, way, way faster whenever it's very close to us. So that's just an angular momentum conservation problem looking at comets for these elliptical orbits. You know, these could work for any ellipse here. And we can do this for, you know, comets, moons, planets, just about whatever, okay? The big thing to remember is angular momentum is conserved. Angular momentum is I omega, and we use point masses for those moments of inertias here, which are mr squared, and then we convert that angular velocity into a linear velocity divided by a position or a radius. Okay, so with that, this problem is finished. So take it easy. Have a good one. Adios. Sayonara. Goodbye. Eric the